Right, to 4.3, read this section. Logarithmic functions. Okay, so I can find a definition. Yeah, I actually write the definition first. So here we go. So the logarithmic function to the base a, where a is greater than 0 and a is not equal to 1, is denoted by y equal to log base a of x. And the way you read this is y is the logarithm to the base a of x. And here's the mathematical definition. So log a of x is equal to y, and this is equivalent to a to the y is equal to x. So you can switch back and forth. So if you have an exponential, you can use the definition to go to log form. So depending on what we're doing, okay? Okay. Real quick, let's write down what everything means, because it looks weird. So log a of x is equal to y. So the x is the argument. The a is your base, and again, the base has to be greater than 0, and it cannot be 1. And this is technically the exponent. Okay, and if you wrote it the other way, a to the y equals to x, well, it's all the same, right? Exponents to y. A is still the base. And this is still the argument. Okay. Real quick, I'm just going to show you what they look like. Delete this from last night. Let me just pick a random one here. Y equals 2. Well, actually, hold on. Yeah, that should be okay. So 2 to the x is the exponential, right, which we talked about last time. And if we use y equal to log base 2, right, use the log definition, you see how they're inverses, right? You look, they're pretty much the same, but they're inverted. So kind of like the x squared and square root. They're inverse functions, and they will undo each other. Both of them are to the base 2. Okay. Okay, so do our first example. So evaluate the following logarithms you may need. Well, yeah, I'll just write it down. Use this property from exponents. A to the x is equal to a to the y, which implies that x is equal to y. So if you have this equation, then that means the exponents have to be equal to each other. Okay, so that might come up. Let's do part A. So it says log 2 of 8 is equal to 3. So here it's not really, there's nothing to really solve, but what I want you to see is you can use the definition so it can make more sense. Because when you first look at these types of questions, it just looks strange, right? So you can use the definition here to rewrite it. So this means, right? So 2 is the A, y is the 3, and that is equal to the x, right? So we know that 2 cubed is equal to 8. That is what this is saying, basically. Okay, but in logarithmic form. So log base 2 of 8 will reduce to just a 3, because it's asking what is the power on the 8. Another way to think about it would be to rewrite it this way and change it to a power of 2, and then realize that these will cancel out. So these will leave you only with the exponent. Okay, so there's two ways to think about it as to why this happens, why that happens, and why it's true. Okay. So what I want you to do on these types of questions is just rewrite it as a power that matches the base. So for example, let's say it was 100. Right, so right because of the 10, that would be a log base 10 of 10 squared, right? Because 100 is 10 squared. So now that these match, you'll end up with just the 2. So when you do these, just try to make it match the base. Whatever argument you have, change it to this base. I think that'll be the best approach. Okay. Do one more, a couple more. Log base 3 of 81. Okay, can I rewrite 81 as a power? And if you can't see it, just try multiplying 3 a bunch of times, or the base. Okay. Just say, you know what, I don't know what the heck 81 is, but you know 3 to the third is 27. 3 squared is smaller, so that doesn't make sense. 3 to the fourth is 81. So that means that I can rewrite this guy as log base 3 of 3 to the fourth. These will cancel out, right? Leaving you with just the power. Does that make sense? How to approach these? Okay, this is something a little harder. Let's say they're fractions. Let's say it's log base 4 of 1/16, the 16th. So we know that this is technically a 4 squared on the bottom, right? So what you can do, change it into a fraction, or leave it as a fraction, but change the lower part into a power of 4. So now it's almost ready to cancel. So what you need to do is to rewrite it as 4 to the negative 2. Okay. So then these just cancel, leaving you with negative. Same thing for decimal. Let's say you had, I don't know, base 10, but you have a 0.01. Right? This is technically power of 10, right? That's 10 to the negative 2, I believe. Or in other words, this is a 100th, right? 1/100. So there's a couple of ways to think about this. You can change it into a fraction if that makes more sense. Or you could be, because remember, 1 divided by 10 is 1/10, right? That's where the name comes from. 1 over 100 is 0.01, so it's going to be a 100th. So we can just change this into a 100th, and then change that guy into a 1 over 10 squared, which is 10 to the negative 2, right? Like we did the last one. Anyway. That makes sense, that property. So if the bases match, you just cancel. That's it. All right. Example 2, we'll just do a few. Use definition to change exponential to log. So 3 squared is equal to 9. The log form would be, right, this is the base, so that's going to be log 3 of the argument x, and the power to be equal to 2. Okay? So in the homework, I'll just have you convert it. So 2 to the 5th equals 32. The log form would be log base 2 of 32, which is equal to 5, using this definition from the beginning. Okay? All right. You guys okay on example 1 and 2 so far? I go in the other direction. Change each log to exponential. So part A, the log base 7 of 1 is equal to 0. So the exponential form would be 7 to the 0 is equal to 1, using the definition. And I'm going to write the definition up here if you forgot. This is what we're using. All right, just going back and forth here. Okay. Let's do a harder one here. 5 to the negative 3 equals 1 over 25. So this question, the log would be, leave a space. The log would be log 5 of 125 is equal to negative 3. Part C, 6 to the 1 is equal to 6. So the exponential would be log 6, right? Base 6 here, of the argument 6 is equal to the exponent 1. So I'm just using this over and over again. Does that make sense? Okay, keep going then. Something else. That's nice, but exponential and interesting. So that log just log 4 of x is equal to 2. So the base is 4, the power is 2, and that is equal to some x. Right? Definition. Base a equal to y, that's the power, and then equal to the argument here. So let me give you all the properties because I've been using them in the background. So it's more appropriate that I give them all to you now. The property of logarithms. So in the list below, a is greater than 0, a cannot be 1, also x is greater than 0, and r is any real number. Here are all the restrictions for the variables we're going to use. Definition, we've already written this before, but here it is one more time. It's all in one place. Log a of x is equal to y, which implies that a to the y is equal to x. So property 1. If the bases match the argument, or actually log of any base, a, if you have a 1 inside, it will always be 0. Number 2. Log a of a, they will cancel out, leaving you with the number 1. All right. Okay, number 3. If you have the base a, but then you have a log as an exponent, which looks weird. Since they are inverses, they will cancel, leaving you with the argument, and vice versa. Well, now before we get to that, number 4 will be log a of a to the r, which is equal to r. Vice versa, we were saying that log a, oh yeah, that's right. Yeah, I already got it. Sorry, I got paranoid. We're good. All right. So these are all our properties with that definition. Okay. Go ahead and write some more properties actually. So I can have all in one spot. Enough, like the book likes to separate it, but I don't want to do that. Here are more properties here. So the product rule, call it number 5, I guess, is when you have a product inside of any base, x times y, that will become an addition of two products there. There you go. So this is product rule. Number 6 will be the quotient rule. So if you have a quotient or something being divided inside, x over y, that will equal log a of x minus log a of y. Okay, and then the power rule. If you have a power on your argument, I believe they write it this way. You can bring the power down, the r, up in front. Or if you have a number in front, you can bring it up. Either way. This will be the power rule. All right. Okay. So let's do an example for it here, just a couple of them, using the first set of properties. So example 4, let's see, some simple questions. I forgot the name of it though. we'll just call it simplify the logarithms. So part A will be log 5 of 1, right? So using property 1, we know that if there's a 1 in there for any base, number 1 says that will be 0. So this is going to be 0 for this question. Doesn't matter what base it is. If you put 22 down there and a 1, it's still 0. Okay? Part B. Now, you said if they match, right? You have a 4 and a 4. Well, that would be 1. I don't know why I wrote B twice. D. If you have a power raised to a logarithm of the same base with an argument of 81, we know that these will cancel, leaving you just the argument, nothing else. Okay. Do one more of these. Log 8. Oh, actually, yeah, that's fine. Log 8 of 8 to the 1.2, right? So again, just like this guy, if they match, they will cancel out to be just 1.2, just the power. Okay. All right. You guys okay so far on the basic properties of logs? Okay. I mean, your silence means super easy or something. Right. Example 5. Use the properties. Of logarithm to find the exact value of each expression. So these will be a little harder. This is when you have to apply the properties. So for example, let's say part A says log A of base 8 of 2 plus log 8 of 4. So if we use the product property, we showed that addition can be changed into a product, right? You see what I mean? So we have addition. So whenever you see two logs being added together and the bases match, then you will get the same base with the product of both arguments, 2 times 4, which gives us 8, right? And then the first of the property says, if these match, you're left with just the power And since the power is 1, they just completely cancel, right? Nothing else to do. Next one, log 6. So 9 plus log 6 of 4. Right, so the bases match. So multiply these products, these arguments rather. 9 times 4, which will be 36. And we know that 36 is just 6 squared, right? So these will cancel, leaving you with a 2. Okay. You guys have any questions on the product property so far? That's what happened in between. All right, let's do a subtraction. So log 6 of 18 minus log 6 of 3. So that will be, since it is subtraction, we will divide them instead of doing a product. So 18 divided by 3 gives us a 6, right? And now they match, so I'm left with 1. Nothing else to do there. Okay. Let's try the power rule. So log 2 of 16 squared. It looks like it's too far away. Okay. Log base 2, that's 16. So we know we can bring the 3 in front using the power rule, right? Then we can just deal with that 16 ourselves and change it to a 2 to the 4th. So this will cancel, leaving me with the 4, but that 3 is still there waiting for me. The answer would be 12. Okay. All right. Down to 6. You guys okay so far? Just let me know if I'm going too fast or something doesn't make sense. All right. Write as a sum of logarithms. Express powers as factors. Okay. So basically what you want us to do is expand everything into sums. Let's say it's log base 2 of 5 times 3. Right, so since it's a product, you would separate into log base 2 of 5 plus log base 2 of 3. And that's all you do. You just separate them using the product rule. Now, if they have complicated powers, you would separate them using the product rule. Then you would deal with the powers using the power rule. So if there's a 3 on there, you bring it up front. There's a 5 on there, you bring it up front. And that is the power rule. Okay. Let's do some expansion of quotients. Right as the difference of logarithms and again express the powers as factors. When they say that, all they mean is bring the powers down. No, don't leave them up top. Log base 2 of 5/3 will be log 2 of 5, that's the top part, minus log 2 of 3. So if you see a fraction, or in other words, a quotient, separate them. So let's separate another one for the practice. Sorry about that, put those off. Log base 5, so you put the top one first, minus the bottom part. And of course, the bases will stay the same, base 5. This is my quotient. Then, bring the power in front, and you're done. And that's it. That's how you expand all the way. Power rule. So first step, we use the quotient to change into subtraction. Then we brought the powers down using the power rule. Okay. So we're just practicing using all the properties. That's what the 4.3 is all about. It's just what are the properties, how do you use them, and then practice going backwards and forwards. Okay. Now let's go the other direction where we combine them into one function. So now let's do, let me see here. Let's do a more difficult expansion first. No, it's working on the another page, it's fine. I'm trying to give you many examples so it's not too difficult. Write as a single, write a single logarithm as the sum or difference of logs. Okay, so here we go. So just expand all the way. That's what they want. 4x over y. So notice how there's two factors on top and one on bottom. So you should do this in pieces. So first separate the quotient as the top part minus the bottom part. So that's quotient rule right there. What we applied. Then, right after that, apply the product rule to the 4 and x. And then that y is still there. So that's product rule. You see how we expanded the top numerator and bottom denominator, right? As 4x minus y. Then we separated the 4x into 4 plus x. So these are all properties of logarithms. So if you have any questions on part A? Okay. Let's do one more and then we'll go to combining logs instead of separating. Cube root of x, y cubed, I guess. So let's start with the quotient and go from there. So this will be log 8 of the, actually we'll change that to a power right now, x to the 1/3. The cube root is the same as a 1/3 power, right? Minus log of the bottom part, log 8. So that was my quotient. Okay, so now we'll just bring down the powers and we're done. So this will be a 1/3 log minus a 3 log 8. So we did expansion with all the rules, and then we did multiple rules at the same time. Now we're moving on to the combination. Okay, here we go. Okay, so example number 9, you have 2 log 10 of 5 plus log 10 of x plus log 10 of y. So see how they're all separated, right? They're all sums. All the bases match. That means I can combine them. But you do not combine until all the powers are up top. So there's a 2 here. So we first have to deal with this. So I have to write the instructions. Write each expression as a single log. So we wrote 2 log 10 of 5 plus log 10 x of x cubed plus log 10 of y. Okay, so then you bring up the 2, the first thing you do before you apply the product. Okay. So from here to here, we used the power rule. Then we combine. I recommend combining 2 at a time because this is new to you, maybe. So let's do these first 2. Log 10 times the log 10 of this argument times that argument. And then we'll do this one in the next step. So that was product rule. Okay, then let's go ahead and change that to a 25. That's a 5 squared. It'll be 25 x cubed times y. So we combine everything into one single log. Okay. Are there any questions on part A? Okay, another one. Go harder one. 2 log base 2 of x plus 6 plus 1/3 log 2 of y minus 5 log 2 of z. Okay. So first thing we said, deal with the powers, right? You want to bring that 2 up, bring that 3rd up, bring this 5 up. I'm going to leave it negative because we're going to use that as a quotient rule. So here we go. So log 2 of x plus 6 squared plus log 2 of y to the 1/3 minus log 2 of z to the 5th. So I applied power rule to each single one. Okay, so then we're going to deal with the plus and the minus. Here we should definitely do 2 at a time because they're not all the same sign. So these two being added together means you change it into a product. And y the 1/3 is just a cube root of y, right? Put brackets on this. Minus log 2 of z to the 5th. So from here to here, we use the product rule. So then this will become a quotient, right? Because of the minus. So this argument will be on the bottom. So the final answer will be x plus 6 squared cube root of y over z to the 5th. So all of this nonsense is combined into a single logarithm. Okay. Now we're about finished with 4.3. You guys have any question on example 9 or 8 before I do the last part of this section? Okay. All right, so let's talk about the natural log and the common log. So on your calculator, they have the log button. So if the base of the logarithm.
Can you move the paper up a little bit?
Sure.
Thank you.
There you go. So if the base of the logarithm is 10, then we call this the common log. Then we have the common log function. We write it this way. So on your calculator, they just have the log button. If you see something like this, I'll check it out. My calculator here. So if I hit the log button, see how there's no base there? You guys see that? I don't know if that's too small. If you see no base, that implies the common log. So if it's written this way, then it's base 10. So if I were to put a 10 in there, remembering our properties, these should cancel, leaving me with a 1, right? So common log means they don't write the base. Kind of like the square root, right? When you see the square root, they don't put the 2. It's implied if they write nothing. You know what I'm saying? It's just shorthand. Now the natural log has its own shorthand. So if the base of the logarithm is e, then we have the natural log function. Okay, so here's in plain English, right? Common log means this. So log base 10 of some x is just written this way. Log of x, right? natural log, which is the special number e, base e. So they don't like to write the e, they just go ahead and say ln of x. That's all they're saying. And of course, the exponential form would be x is equal to 10 to the y, and this guy would be x is equal to e to the y. Anyway. I don't know if I wrote that. 1 second. Make a bigger note here. Y equals log x implies that x is equal to 10 to the y equals ln x implies that x is equal to e to the y. Okay. All right, so one last note and then we're done with 4.3 is the change of base theorem. You might have like one question on this. It's not hard or anything. Just follow the formula. So if you have a log of base a of x, you can just change that log to ln of x over ln of a. So let's say there's a weird a down here that you don't want to deal with, or it's not on your calculator. So you know what, I have ln on my calculator, so let's just change this instead. So for example, if you had log base 5 of 7, you'd say, you know what, I don't know what the heck that is, but I can use 7 ln 7, and ln 5, and find an approximation using your machine, right? So it would be ln 7, that fingered it, ln 5, 1.2-ish, whatever. Okay, so that's 4.3. You guys have any questions or issues with any of the properties of, or the definitions of log, the properties of logs, the definitions, etc.? So on this section, we're actually going to solve stuff. Last section, we were just applying properties. That was it. So logarithmic and exponential equations. So let's start with log equations. So solving log equations. Okay. There's a few ways to do this. So solve log base 5 of x equal to 2. So basically they're asking what power of 5, or what number or what power of 5 would go in here for the x to give me 2. The only thing you can do, the way the book and the homework will recommend is to use a definition. So remember we said that this is the base, right? This is the power. So x would be 25, right? So that would be using the definition. What I prefer to do is just to take the equation and make those your exponents, and you set it to the base 5. So you put 5 there, and you put a 5 here. So 5 to the log 5, 5 to the e2. Okay, so then these will cancel, leaving me with x equal to 20, x equal to 5 to the second power, which is 25. You can do it either way, but this will be more useful later. Okay, so for example, let's do another one. So ln x equals 3, well, if I make e the base, then these cancel, and you're left with x equal to e cubed. It's just some decimal number. I don't know what that is. It would be e to the third, like 20.08. Okay. But same deal, even if the argument is more complicated, nothing really changes. So if you have log 2 of 3x plus 4 equal to 4, bring the 2 as your base. Right, so use cancel, leaving you with 3x plus 4 equal to 2 to the 4 is going to be, what is that? 2, 8, 16. Yeah. So then you just solve this basic equation, right? Solve for x. So subtract 4 on both sides, right? I'm going to write it one more time. So minus the 4. You get 3x equals to 12. Divide by 3. And x is 4. But you should check when you're solving logarithms, because if your results, if you're not able to plug in the results, then you should not be using it. So 3 times 4 plus 4, is that indeed 4? Well, that would be 3 times 4 is 12, plus 4 is 16. Yeah, that would be 2 to the 4, right? Which cancels out to 4. That makes sense. Okay. Make sure you always check these, okay? One more. Log of x plus 9 is equal to 2. What you can do is just introduce the base 10, right? Because that's the common log. So just bring in the 10 and make that your base, and then use the 10 on both sides. So this becomes 100. These cancel, leaving you x plus 9. Subtract the x and you get 91. Okay, don't forget the property that we're using, right? If log a of a to the x, if they match, you're left with this, right? So recall the properties in case you're wondering why this is working out, right? It's because of these properties here. So a to the log a of x leaves you with x. Okay, you guys cool on the first four? Does that seem all right? One second. Okay. Let's do a harder one. This will seem a little easier. This guy. A little harder. So 4 ln x is equal to 12, right? So I can't use that idea, right, to cancel the log because the 4 is in my way. There's a few ways you can go about this. You can move the 4 upward as a power, or you can divide the 4 out, right? Either way. Doesn't really matter. So we can divide both sides by 4. So ln x equals 3. So then introduce the e. E cancels ln, right? So here to here, introduce base e to match the log base, right? And then they cancel based on the property. You're left with x equal to e cubed. There'd be nothing else to do. Does that make sense?
Could you show the other way that you said, so you said to divide by 4 or?
Yeah, let's try it. You're saying like just move the 4 up as a power? So let's do an alternate method here. So just real quick, e cubed, I don't know what the heck that is, so let's write it down. Oh man, I'll put a plus in there. E cubed is 20.08, right? So we'll remember that. Now, if we go the other route, using the power rule first, bring up the 4, right? This is a power rule. Then introduce the e. So then this would cancel, but now I have x to the 4th equal to e to the 12th. So I would have to 4th root both sides. In order to solve for this. I mean, we can reduce that because remember, 1/4 root means what? 1/4 power, right? And if you have a power to a power, last week we said you multiply using the rules of exponents. So 12 times a 4th would be e cubed. But you could just leave it this way and say, you know what the heck is e12? Everything to the 1/4. Yeah, see how it's still the same? And as you can see, it's simplified to the same anyway. But I would advise that if it divides evenly, just go ahead and do it. Why not, right? If it doesn't, then you'll have a decimal here or a fraction. I would leave it as a fraction as you go along. If it doesn't divide, suppose you have like a 5 up here, so you have 5/4 the whole way down. That way you won't have to worry about rounding error. On your homework, if you round something and then you keep going and then you try to punch it in, you may get it wrong. So don't do any decimals or rounding until the very end, assuming there is no exact answer or they asked for a approximate answer.
Thank you. I do have a quick question. So anytime it's ln x, we're assuming that the base is e, and anytime that it's log x, we're assuming that the base is 10, right?
Yeah, it's understood to be that way.
Okay, I just want to make sure. So like for log x, it would never be anything but 10.
Right, like for example, log 2, if you see that written down somewhere, right, that means log base 10 of 2.
Okay, sure.
And same thing for ln2, that would be log base e of 2. So it's always implied. If they don't write it, you will assume 10 or e depending. Okay. All right, you guys have any questions on this one? I'm going to do a harder one where you have multiple logs. This is when you start using the product and quotient rules. I will probably, well, might have enough space here. So now we're solving for stuff, so you don't really need to write anything. No instructions, just solve it. Log base 2 of x minus 2. Log base 2 of x equal to 3. So you need to solve for x, but the x is trapped inside two separate logs. So you got to combine the logs before you do anything. So in the last few examples, we were introducing the base that matches, right? To cancel the logs, but now they need to be combined first. Okay, so log base 2 plus log base 2 means you do a product rule. Use the bracket here. X minus 2 x. So then, now that it's one log, you can combine it. I mean, you can introduce the base to cancel. And everything inside will just come down. These are gone, so you'll be left with the argument x minus 2 times x equal to 8. Multiply this out, you'll get x squared minus 2x equal to 8. Subtract the 8 over, and we can solve this as a quadratic. So we're back to factoring, right? This will be x plus 2, x minus 4. So my two solutions will be x equals negative 2, x equals 4. But do they both work? If you plug in negative 2, you get negative 2 minus 2. And you cannot have any negatives in a logarithm. Logarithms will always be positive. Remember how we defined that the argument must be greater than 0. You cannot have any negatives. So right away, you can't use this guy. So the only solution is 4. You would still want to plug it in, but it's going to work. You would get, yeah, 4 works. So you should always check both. Do you see why negative 2 doesn't work? And do you see why 4 does? Right, let me go ahead and plug it in over here. Log 2 of 4 minus 2, let's check it, plus log 2 of 4, is that indeed 3? Well, this would be log 2 of 2, this would be log 2 of 2 squared. This would become 1, this would become 2, which is 3. So yeah, so let's go ahead and plug it into the original to find out if you get equality. Okay. Let's go to another similar question. Let's do an even harder one here. So you have 3 logs, log x plus log x minus 1 equal to log 3x plus 12. So since there is no base written, we're going to assume it's 10, right? But we cannot introduce the 10 until we combine everything. So if you have one single log on both sides, then you're good. Currently, we are not. We don't have one single on the left side. So that would be x times x minus 1, right? Using our product rule. The right side, I'm not going to do anything. It's there. So from here to here, I apply the product. Now, there's a rule that says if there's the same base equal to each other, you can just set the arguments equal to each other, but I want you to get into the habit of writing this way. Introducing 10 in order to get rid of it, in order to cancel my log. So then you're left with x times x minus 1 equal to 3x plus 12. So then just solve for x at this point, right? So this would be x squared minus x equal to 3x plus 12. Since we have a quadratic, we will move everything to one side like we've always have. So it'll be at so then the factor, does that factor nicely? I hope it does. That'd be negative, oh yeah, negative 6 plus 2. So x is equal to 6, x is equal to negative 2. Right away, I cannot use negative 2 because, let's go to the original. Plugging in a negative 2 would result in a negative inside. You are allowed to plug in negatives as long as it results into a positive inside. Like for example, if you had x plus 7 in here, and you plug in negative 2, you'd have negative 2 plus 7, which is still positive. But we don't have that, so we will only test the x equal to 6. You can go to the original, so test it. I've got a note here. So always put it in the original. Ouch. 6 plus 6 minus 1 equal to 3 times 6 plus 12. So that would be 6 minus 1 is 5. 3 times 8 is 18. 3 times 6 is 18 plus 12. This would be log of 30. And adding logs means you multiply the arguments. So it looks like we're good. We'll end up with log 30 equals log 30. So yeah, that works. So x equal to 6 is the only solution for this example. So sometimes you get 2, sometimes you get 1, but sometimes you get none. And it happens. You should always check. Are there any questions on logarithms? Is it making sense? Okay. Well, we did a few log examples. Let's do some exponent type. So those are all log equations. So let's go to solving exponential equations. A to the u is equal to a to the v. This is the property we're going to be using to help us out. Then u is equal to v. So if you're able to match the base, then we're pretty much good. So we're going to introduce, we can introduce a log to cancel the exponential base. So basically we're going to do the opposite of what we did before. So let's start here. So 2 to the x minus 3 is equal to 2 to the 5. So since they match, you can just set the powers equal to each other, but I want you to get used to this idea. Well, if I want to cancel base 2, I will introduce a log of base 2 on both sides. So then they cancel, leaving me with x minus 3 equal to 5. X is 8. So nothing crazy, right? But if you want to use this, that's fine. But eventually you're going to have to do it this way, because they're not always going to turn into matching bases. Sometimes it's not possible. Let's pick a harder one. So 5 to the x minus 4 is equal to 1/5. So we can still match these guys, right? So we just got to rewrite that fraction. Remember we said if it's on the bottom, you can bring it up to the top, right? And change the sign. And at that point, just introduce log base 5 to cancel the exponential stuff. And we're good. These are gone, and you're left with minus 1. X minus 4 equal to 5 minus 5 to the negative 1. Which is just a fraction, right? Oh shit, that's not right. What am I talking about? It cancels, right? It doesn't come back. So then just add the 4 over and we're done. So so if you can make it match, you just do this and you're pretty much done. So let's move on to stuff where it doesn't match, where it gets complicated.
Sorry, I just want to double check. So we're bringing over the 4, so it's plus 4.
Oh yes, plus 4 would be 3. Thank you.
Well, I just wanted to make sure. Thanks.
Mm-hmm. No, so this guy. 3 to the x equals 5. You see how there's no way I can change a 5 into a 3, right? It's just not going to happen. So you're just going to have to choose a, well, you know what? I think a better idea would be to just choose ln, because if I choose log base 3, at the very end, I am not able to use calculator, or I have to use change of base. So when you notice you can't match them up, choose ln or common log. That way you can use your calculator for the approximation. Over here, I chose whatever I wanted because I knew they would cancel out and I wouldn't have to worry about it. But here, they won't cancel the way I want. So I'll introduce just ln on both sides. And then, remember your, it's right here, introduce ln on both sides. Then, bring down the x using your power rule. So now, oops, no, it's supposed to be a 3. So now, just get rid of that number. Because remember, ln3 is a number, right? It's just like, this is kind of like saying 2x or something. Get a 2x here, you would divide by 2, right? So divide by that number. So get rid of this number by dividing both sides by ln3. You don't have to put the parentheses in, it just did that for no reason. So x is equal to ln5 over ln3. So at this point, that is your exact answer. If you want an approximation, you have to punch in your calculator and do ln5 over ln3. It's about 1.46. 1.465, I guess, whatever. Okay. So do you see how eventually you got to bring the log in anyway, so it's better to just solve it this way every single time. But know that it starts to get uglier and uglier because they don't cancel. Okay. Let's do a difficult one. You guys cool on these first 3 examples? For x minus 1. So we're going to do the same thing, but we're going to have to bring down x minus 1, which is going to make things a little uglier. But there's a few ways to try and make it prettier. So let's go ahead and start by introducing ln on both sides. So the next step, I'm going to bring down, let me make space. 4x minus 1 is equal to ln of this and ln of that. So then you bring down the x minus 1 using the power rule, right? So power rule, and then treat this as just a number, right? I'm going to divide this out so I can isolate that x. That's the whole goal here. So divide both sides by ln 4. So x minus 1 is equal to ln 22 over ln 4. And just add that 1 over and we're done. So ln 22 over ln 4 plus 1. So if they want an exact answer, you'd have to combine these first. If they don't, just do this on your calculator and be done with it. And let's not stress over it. So that would be ln 22 over ln 4, and then just add 1. So 3.229. So that's approximately 3.23. There we go. You see how the properties from last section are going to be important. They're going to expect you to use them at the right time. All right, let's do another difficult one that has weird powers on both sides. Okay. 4 to the x plus 2 is equal to 5 to the x minus 1. Now we'll make this our last example here. So just introduce ln and then try to get those x's down because they're stuck up top and there's no way to solve for them. So bring in the ln. Bring down the x plus 2. Now this is where it gets kind of weird. Here we're going to have to distribute the ln 4 into these guys and ln 5 into those two. So ln 4 times x plus 2 times ln 4. So I distribute those guys. ln 5 times x and minus 1 gives us this. X ln 5 minus ln 5. So now again, the goal is to solve for x. So get all the x's on one side, all the numbers on the other side. So x ln 4 minus x ln 5 is equal to negative 2 ln 4 minus ln 5. So we're almost done. It doesn't look very pretty though, right? We can remove the x from both of these by factoring, and then we can isolate it finally. Make some spaces. Factor the x, and then divide that number off. Oops. So divide both sides by ln4 minus ln5. Whatever the heck that is going to be divided. Some number. So we'll be left with just x equal to this weird disturbing thing over this here. So at this point, all you can really do is put it into your calculator, because it's not going to get any prettier. So it's -2 ln4 minus ln5 over ln4 minus ln5. So it's approximately 19.638. You see how they can get kind of ugly once you have like complicated looking powers up top. So if you can make them, if you can make the bases match, it won't be too bad. But if you can't, well, stuff like this may happen. So just remember, ln4 minus 5, ln5 is just some number nobody cares about. Some decimal. Divide that decimal out, and then find your answer. You guys have any questions about 4.3 or 4.4? Okay. You guys have any concerns with